Good morning, good afternoon, or good evening, depending upon where you are in the world, and welcome to today's webinar, Optimizing Drive Cycle Simulations for Automotive Applications, brought to you by Tech Online, Wolfspeed, Arrow, and broadcast by AspenCore. I'm Chris Keach, and I'll be your moderator today. We have just a few brief announcements before we begin. First, the slides will advance automatically throughout the event. You may also download a copy of the slides by clicking on the green folder icon located at the bottom of your screen. You can participate in our Q&A session by asking questions at any time during this webinar. Just type your question into the Q&A text area located to the right of the presentation window and then click the Submit button. Please note that we'll try to get to as many of your questions as we possibly can at the end of today's program. However, if we're unable to get to your individual question today, someone will get back to you after the program is over. Also, at this time, we recommend that you disable your computer's pop-up blockers, and at the end of the webinar, we will ask you to complete our feedback form. Your feedback will provide us with valuable information on how we can improve future events. You can also launch the survey at any time by clicking on the red survey button at the bottom of your console. And if you're experiencing any technical problems, please type your issue into the Q&A text area, and we will be glad to offer one-on-one assistance. And now, on to the presentation. Optimizing Drive Cycle Simulations for Automotive Applications. Discussing today's topic are Blake W. Nelson, Ph.D., Application and Systems Engineer, Power Modules at Wolfspeed. Blake Nelson received his doctorate from the University of Alabama in 2020, where he studied silicon carbide applications and model development under DoD, DOE, and industry grants. And joining him today is Mohammed Hazaz Mahmood, Ph.D., Systems Engineer, Power Modules at Wolfspeed. Mohammed Hazaz Mahmood received his Ph.D. from the University of Arkansas in 2021, where he studied silicon carbide traction inverter design, development, and validation under ARPA-E, DOE, NSF, and industry grants. It's with great pleasure I now hand things over to Blake to begin. Blake, take it away.
Thanks for the introduction. Today, my colleague Hazaz and I will be discussing how to conduct very long drive cycle simulations, especially targeting automotive applications. And we'll also be discussing our new automotive-focused module, the EAB 450.
Let me begin with a quick explanation of what you'll see in this webinar. First, I'll introduce the EAB 450 and its high-performance reference platform. This module is an excellent choice for traction applications, and its 600 kilowatt reference platform can get you testing on the dyno in short order. Next, I'll highlight some of the many tools available for power electronic simulations, but we'll see that most are inappropriate for our simulation goals. Further, I'll show how to develop an inverter simulation capable of evaluating an entire drive cycle, even one that's several hours long. Next, we'll show you a few details needed to contextualize this inverter model into the rest of the system. And finally, we'll discuss the capability of our simulation to estimate inverter performance, and we'll show how that performance affects vehicle range, battery cost, and more. And finally, we'll show that switching losses are going to be the most important factor in selecting your semiconductors for traction applications.
In addition to giving an overview to the slideshow, I also wanted to give a brief overview of our simulation procedure. First, we start with a definition of our application. This is typically a drive cycle. There's certainly ongoing discussion about which drive cycle or maybe something better than our existing drive cycles should be used to evaluate, say, electric vehicle range. But we think that this modeling procedure is perfectly suitable for things even beyond typical drive cycles. We just think that that's the most universally applicable example today. With the application defined, we then can build a model of the inverter itself. Obviously, this will require understanding the electrical system, as well as some of the thermal and mechanical details. But with those understood, we can then map our drive cycle into electrical requirements for the system. A key component to modeling any inverter system will be a model of your actual devices under test. These models are developed by us here at Wolfspeed, and we're happy to provide those to you. But they were really a critical component in actually understanding the full implications of the system level requirements. Similarly, as far as our modeling procedure goes, just like we need a model of the module to make a model of the system, we also need a model of the device to make a model of the module. So on our side, we were developing layers of models all the way down to make sure that we can provide you with the most accurate information on your system level performance. With that overview complete, let's take it back to the real world. I think that this module we're showing here, the EAB450, is the perfect candidate to help contextualize the simulation work. So this module is really designed from the ground up to take full advantage of the silicon carbide inside it. We start off with a very low internal inductance of only 6.7 nanohenries. We also have an offset terminal design, and that is going to give you an even easier ability to use proper bus work on this module. And so it helps us keep a low inductance all the way back to your capacitor bank. With that, you can get a system inductance much lower than many comparable power modules. Similarly, with the thought of high performance in mind, we use silicon nitride as our substrate. That gives us a great both thermal performance and mechanical robustness for vibration. Many features are built into this module, such as voltage sense for your DSAT protection and an NTC you can use for internal temperature feedback. And finally, this platform is designed for both 12 and 1700 volt silicon carbide devices, which makes it an excellent candidate for all sorts of high performance automotive applications. Let me once again highlight the advantage of having a very low inductance between your buswork and your module. In traction applications, you're almost certainly going to be switching loss dominated because so much of your utilization is that light load. Bus inductance is going to be a big factor in your actual realized switching losses. Why? Well, your bus inductance is going to lead to voltage overshoots, which are linearly dependent on your DIDT, which, again, is going to determine your switching losses. High DIDT, low switching losses, but high DIDT, high overshoot. With a lower inductance, your relative ratio from DIDT to overshoot goes down. So we want to encourage the best possible layouts we can and come up with ways to minimize those parasitic inductances. The XM3 was designed from the ground up to fully take advantage of silicon carbide, and it really has a major advantage in power density over traditional modules that are legacy from the silicon days. Our partners at Lucid really took advantage of this extremely power dense module in their design of the Lucid Air. As you can see on the left, the traction inverter and motor combination is extremely small, weighing only 74 kilograms. With over 670 horsepower, this makes it one of the most power-dense traction drives in all production electric vehicles. While I think we would all love to expense a Lucid Air to our test budget, I think there's a more practical solution. Here we're showing our XM3 dual inverter reference platform, which is an excellent starting point for anyone looking into silicon carbide traction applications. This is a complete inverter system with both closed-loop control and very easy integration into existing liquid cooling setups. While the outputs can be used separately, together they're capable of producing 625 kilowatts continuously. All of that in just 8.6 liters weighing 9.7 kilograms, leading to an extremely high power density. Our previous reference design had already surpassed the typical power density we see in silicon inverters, and here we've more than doubled its power density. I'd also like to point out that we didn't have to compromise efficiency in order to achieve this very high power density figure. As you can see, we were still able to achieve over 99% efficiency with this reference platform. With our reference module introduced, I'm now going to talk about how we can develop inverter models which are suitable and appropriate for very long drive cycles, usually longer than 30 minutes. As you can probably imagine, you really need the right tool in order to simulate 30 plus minutes in a drive cycle scenario, especially considering how complex inverters can be. The power module team at Wolfspeed uses a lot of different tools in order to help us understand and characterize the performance of our modules. Before we dive into the specific methods we're using for drive cycle analysis, let me give you just a brief overview of some of the many different tools we use. For example, we have FEA tools, or finite element analysis. These tools are very good at doing geometrically dependent things, such as more detailed thermal analysis or perhaps deriving inductance from a CAD file. While they're very powerful, they're extremely slow. And clearly, they're not the tool you want to use for a circuit level simulation. I think most people would think of SPICE first when I mention circuit level simulations. SPICE simulations are great, but they have their own limitations. Specifically, because SPICE level simulations try to derive the current and voltage at every single time step, you're going to run into situations where they are unreasonably complicated in order to do very large inverter models. Even in the case where you develop a particular behavioral model which is fast enough for an inverter, you're still only going to see simulation speeds on the order of milliseconds simulated per second. So you're going to need an unreasonable amount of time in order to do something like a drive cycle simulation. Plex, once again, steps the simulation complexity down a bit from SPICE. It's going to use a more idealized form of the MOSFET in order to really speed up simulations. But even it is not perfect. And we've actually made a few modifications and built on its tools in order to help us achieve these very long simulations. While Plex is making those simplifications in order to run a bit more quickly than traditional tools like SPICE, I think you'll find that the simplifications were made very carefully in order to not compromise accuracy in the particular realms Plex wants to simulate well. For example, rather than calculating the switching losses from a very detailed transient model like you would do in SPICE, it uses a lookup table which actually takes the datasheet information and inserts that switching energy into the thermal system at each switching event in the cycle. Not only is this so much easier to model, it also leads to a much faster model. You'll find that there are similar simplifications, such as using a lookup table for conduction losses and a Cowher network for the thermal model. All of these are very intentional simplifications, which, while of course you're not going to be able to look at very precise transient events inside the Plex model, allow you to do things like model controls without having all this extra cumbersome model weight, just leading to more CPU cycles used for nothing you really need to know. What that means is that Plex can't do everything, but what it does do, it can do very fast. And it's often even more accurate than a poorly made SPICE model. While we may be leaving a lot of information behind, for the most part, those particular factors aren't going to play in system evaluation as a whole. Similarly, the dynamics which are captured by Plex are very helpful in doing things like developing your controller. And Plex has all sorts of tools for creating a custom control model inside of Plex and then linking that to other tools which will help you deploy your control system onto a DSP or microcontroller. Another great use for Plex is being able to predict your actual junction temperature rise in application. Not only does this help you select the appropriate product for your use case, but it'll also help you determine impact of system design decisions, such as switching frequency changes or even RG changes. And of course, you can use Plex for drive cycle analysis. I do want to spend just a little bit longer diving into what the simplifications being made in Plex are, because that'll help us understand the pros and cons of the different modeling approaches in Plex. When most people think of Plex models, they're kind of intrinsically assuming what's called a switched mode model, where we see an actual switching event being simulated every time you change the gate signal to the input of the device model. As you can see on the output voltage waveform, this leads to a idealized square wave, this being because Plex does not attempt to simulate that transient event. It actually walks right up to that point and simulates the kind of instantaneous time step before it. And then it switches all the electrical conditions of the simulation. It injects that switching energy into the thermal system, and it simulates the next point of the switching event. So you can imagine that it's actually just taking a very complex thing, the transient, and only using 2 points to simulate it. This is part of the reason why Plex in general is so much faster than a SPICE model, because as the SPICE model goes through that transient, it'll need thousands of points in order to track the voltage and currents as they change. Now, you can already imagine some of the simplifications this is going to lead to. Obviously, your rise and fall times in Plex are going to be completely unrelated to your model. They actually just come down to what your simulation time step is. And with this kind of information eliminated, you really can't simulate device transient behavior. Think of overshoot at the voltage node. Those kinds of parameters, which are dependent on the transient behavior of the MOSFET, are going to be completely ignored in Plex. Still, just because we're eliminating some of those transient dependent behaviors, that doesn't eliminate all of the factors from the simulation. For example, you can capture the low frequency dynamics such as ripple voltage quite easily, as those are independent of the specific MOSFET transient events. Unfortunately, despite how much simpler Plex is than a SPICE level simulation, we still have an issue where we're attempting to simulate thousands of transient events in a single second due to the high switching frequencies achievable by silicon carbide. And we have thousands of seconds in our 30-minute long drive cycle. So between those two factors, you really are only going to be able to hope to achieve a maybe second per second kind of simulation in Plex. That's already quite fast, but when you have a 24-hour drive cycle or some other crazy thing, you'll find that there's a huge limit on your capability to simulate those without just tying up your computer for the next few days while you go do something else. Fortunately, there is a solution. Plex offers what's called an average model of the half bridge, and this is significantly faster than your typical switched based model. So this makes Plex behave a bit more like Simulink, if I'm allowed to say that, in that you're simulating the output phase node of this half bridge with two voltage sources, which are going to be linearly dependent on both the input voltage and the kind of averaged duty cycle of the gate wave forms. So you can either put in kind of a natural gate wave form into these models, or you can average your gate into a duty cycle, and the time average model will behave the same in either case. This output does lead to some simplifications. Again, you're realistically going to be eliminating your ability to simulate things like ripple voltage, but we don't necessarily need to know the ripple voltage across an entire 30-minute drive cycle, right? We can take a few compromises on those accuracy points because we don't need the full detail at every second. We can simulate the inverter for a short time length with more detail and for a long time length with less detail. There is, however, one compromise that is really not tenable for what we want to try to do with this model. The built-in Plex averaged model does not have thermal capabilities, and that leads to some pretty big compromises in terms of what we'd like to do with the model. For example, we would want to accurately predict our energy usage by the inverter in a typical drive cycle, but because the average model doesn't consider losses or junction temperatures, you really can't do that as is. So the rest of my portion of this talk will discuss how we kind of tack those features back into the average model to give us the best compromise between simulating the things we want, but removing as much of the excess weight from the simulation that we don't need as we possibly can. So first we're going to calculate turn-on losses. This very simply uses a number of parameters which are derived from the average model, and we take them and feed them into a 3D lookup table. I'll go into more detail in just a moment, but the output of that lookup table is then scaled by RG. This might be very familiar to you if you've ever built a Plex model, in that a very typical way of developing the switching losses for a Plex model is to give it a table of all the different operating points you find in a data sheet, and then adding a scale factor for RGs outside of that table. So we can basically imagine this as a recreation of the Plex model. And as you can see, that lookup table for us is coming directly out of the Plex models we publicly provide on our website. So this information is basically mapping that traditional Plex switch model into the time averaged model. We do almost the exact same set of calculations for the turn off losses, just obviously using a different lookup table set and a different scale factor from RG. Conduction losses are just a little bit simpler than the turn-on losses and turn-off losses. Obviously, they're not going to be dependent on RG, but the lookup table is actually only dependent on the device current and the current junction temperature. So the lookup table will then give us the actual voltage drop, and we multiply that back through with the device current, and that gives us our conduction losses. Finally, we need to sum all the losses together to get total losses. Of course, we need to scale the turn on and turn off energies by the switching frequency in order to get to switching losses. In this case, we're using a fixed switching frequency because our controller is not going to be changing switching frequency. But if you do have a control algorithm which changes switching frequency, it's quite easy to pull that output into this calculation, and it'll adapt over the course of your drive cycle. So not a complexity we had to deal with, but certainly can be integrated into this model. Finally, just to mention, we're doing the same conduction loss and switching loss calculations for the diode, but they aren't shown here just for brevity. Of course, an input to almost all of the blocks in the last slide was TJ, which we need a way to calculate. The simple answer is that we are using the power loss to drive a little custom thermal simulation. You know, it's just going to have a model of the power module's thermal impedance plus an external RTH, which kind of represents that thermal resistance between the case and the fluid. We have a fluid temperature as well. And we can use that to derive our current junction temperature. This has to be done for each switch position. So this is just one, but there are multiple. To explain a bit better about that Cower model, it's actually a representation of the datasheet ZTH provided in all our module datasheets. And it's just a very simple representation of the kind of thermal transient response of the power module. And it helps, smooth out the peaks you see at the, output frequency of the inverter and gives you a better representation of your realistic junction temperature. With our junction temperature known and our full loss system calculated, we can kind of integrate this all back together into a complete model of the inverter. So, of course, we have our electrical system. You see the 3 phases there, which is the particular number of phases in the inverter we were modeling. And inside each one of those module blocks I'm showing in this model, it's one of the averaged models that we discussed a few slides ago. Next, I'm showing our representation of the thermal system. We have a separate block for both our loss calculation and the thermal system itself. Inside that loss calculation block, of course, we're pulling information out of our averaged models, from the phase. So the electrical parameters are an important feed-in into this loss calculation. The most important output of the loss calculation is, of course, that total loss, which we're feeding into the thermal system, which feeds out, our junction temperature. And, of course, the junction temperature has to be fed back in to our loss calculations. Finally, to finish off the electrical model, we really need a model of the load. There are more than one way to go about doing this. Of course, you could have a very detailed motor model, which tries to calculate out your currents at any particular event, but we have actually simplified this down into a Excel spreadsheet, basically. So we have a table of our time, torque, and then that calculates out the different current magnitude vectors. And so Hazaz will go into more detail on how we're actually kind of making the assumptions required to get here. But the core idea is you can basically use a known waveform, whether it's measured, whether it's calculated, and force that back into these models using an ideal current source. And that will let you calculate your losses in a modeling sense for any, drive cycle. WLTC was chosen just as a representation, but of course it's not limited. We've already done many drive cycles ourselves, and it's basically whatever you can come up with the correct calculated currents for, you can simulate in this manner. Finally, of course, to accurately model the system, you need some representation of the controller. It's really unfortunate, but we don't have time to get into what we did on the control side. There are, simple controllers built into Plex to get you started, but the important key here is we have some of the references pulled from that Excel data set, and it's feeding into the inputs of our controller. And of course, we use those gate signals to drive the system. I will say one final note on this whole system. We did simplify and only calculate the losses in thermal for one phase, and we used that, scaled it out to all three phases. Because of the way we calculated our phase currents, this is a completely fine representation of the system, and it helped us save a little bit of time on our total simulation time. But it is a compromise. It's not necessary. You could certainly simulate each phase independently. There's no problem with that. It'll just be slightly slower. And you kind of have to decide the accuracy versus speed trade-offs and, what's worth it to you in your modeling goals. All right, that concludes my part of this slideshow, and I'll pass it off to Hazaz to give you a bit more of the details.
Thank you, Blake, for your presentation. Welcome everyone again. This is Hazaz Mahmoud, and I'm currently working as a systems engineer in Wolfspeed. I'll be talking about the drive cycle simulation with XM3 Wolfspeed power module. First, we'll be discussing about the vehicle level simulation flow. Vehicle level simulation has three major parts or components which are dependent to each other. First one is module level modeling, which contains SPICE or Plex model of the MOSFET and internal module parameters and parasitics. Next part is system level simulation or converter model, which contains converter model in Plex, loss model, and thermal model. Our previous presenter, Blake Nelson, already presented regarding the loss model development and thermal modeling as well. And the last part of the puzzle is vehicle level simulation. So what we are trying to do here is when an EV is driving around, how that's affecting the converter and silicon power module, which is basically power dies. As a silicon carbide manufacturer, we want to figure out how the stuff happening on the most right part is affecting the most left part of the flow. This information can help us to develop the best silicon carbide power module for EV industry by observing the effects of the operating conditions of EV on the power modules. Before going to the drive cycle simulation, let's talk about the busbar modeling. Busbar modeling is a very important part of the overall system development. Overlapping DC busbar is effective to reduce the strain inductance of the overall system. Our XM3 module is designed for easy connection of the overlapping busbar by introducing offset terminals. Now, how and where we are going to use this busbar strain inductance information? We are going to include this busbar inductance information to determine the external gate resistance RG, which affects the silicon carbide power module switching loss directly. The RG later on can be used to determine the desired dVdt or dIdt. Now, after the busbar concept development, a CAD model is designed, which is shown on the slide. Later, this CAD model is used to simulate the strain inductance of the busing structure. Any FEA tools can be used to simulate this. Here we have shown the Q3D simulation and their results on the slide. Another way to validate the inductance of the busbar is to do a quick prototyping using PCB to replicate the geometry quickly and cheaply. The impedance analyzer can be used to easily measure the actual strain inductance. If the inductance value doesn't meet the requirement, then this busbar modeling process can be iterated multiple times to achieve the desired number. By designing in such way, our XM3 inverter busbar could achieve around 2 nanohenry strain inductance. Now, when we have the full inverter designed, we can put this into different test conditions and validate its performance. Since the XM3 inverter for traction application, a drive cycle can be used to validate its performance. The information obtained from this driving profile simulation illuminates some very important information, such as the junction temperature distribution over the full drive cycle. This can be helpful to understand the life cycle mission profile, which can be fed to the reliability model. This can also predict the reliability of the module interconnects under a specific driving condition. So we take the car mission profile, we determine the temperature distribution, and then this temperature distribution is fed into the lifetime model to estimate the lifetime. Another information that can be analyzed from this simulation is the energy allocation. We can determine where the energy gets lost for this silicon carbide power module for a certain mission profile. This information helps us to develop optimized silicon carbide for traction application. For sizing the module or increase the ampacity of the module, it is important to optimize the module for conduction loss. However, from the drive cycle simulation, it is very clear that during normal use or operation, the silicon carbide users are taking the big bite by the switching loss, since current needed for the drive cycle does not even reach close to the module rated current. Therefore, they are affected by the switching loss significantly. Hence, optimized module for switching loss is desirable for efficient traction drive. All this information that are collected from the simulation can be used to determine the effects of the switching energy loss. Switching energy can be translated to battery range or potentially weight savings. With right numbers, it can be translated into dollar savings as well. All these benefits can be achieved by adopting optimized silicon carbide for traction application. On these slides, the drive cycle simulation workflow is shown. To be noted, a significant amount of OEM companies follow similar workflow for drive cycle simulation. Here, the purple color band represents the information provided by the customer, and orange color band represents the Wolfspeed model that we developed to simulate the driving profile. In general, customer provides torque, velocity, etc. information as drive cycle. Then these information are translated into simulation operational points based on machine parameters and operating conditions. Then the closed-loop loss model and thermal model is incorporated to simulate the whole drive cycle, which is shown earlier by Blake. In this slide, on the left, a general worldwide harmonized light-duty test cycle, which is also known as WLTC, is presented, where there are 4 sections of operation: low speed, medium speed, high speed, and extra high speed. On the right, it is shown what are the electrical parameters are translated from WLTC for simulating this driving profile. Let's talk a little bit more about the WLTC and how that drives the silicon carbide power module design aspects. There are 3 major sections in this figure. First, the average WLTP condition, which is very light load. Typically, this drives the range of the vehicle. If we want to optimize range, we have to look at this average WLTP condition. Now next we have the peak WLTP condition. This gives us the information about the delta T, which can be used to estimate the lifetime of the module. However, this peak WLTP condition only uses less than 30% of the available thermal performance. Last section is the peak sizing condition, which helps to optimize the performance of the drivetrain. Today, a traction drive is designed, the focus is on the peak sizing condition. However, if we want to optimize range and cost savings, it is very important to focus on the average WLTP condition. In this condition, major energy loss contributor is switching energy, since it is light load condition. Therefore, to achieve better range in addition to the performance, switching optimized silicon carbide like XM3 is unavoidable. Now let's see some of the simulation results and what can be interpreted from the results. This slide presents the single XM3 module ampacity, where percentage of the switching loss and the percentage of the conduction loss and the junction temperature versus peak currents of the module is shown. As stated in the figure, it is so obvious that at high current, the conduction loss is much higher than the switching loss. However, if we consider a typical WLTC cycle, which is shown in the right top figure, the peak current never exceeds more than 200 amp. From this piece of information, it can be determined that the switching loss is the major contributor of the total loss for the WLTP cycle. Therefore, switching loss cannot be ignored while sizing the module, especially if the module is for traction drive system. This is where the Wolfspeed's XM3 silicon carbide shines, since this is a switching energy optimized power module. This figure shows the converter output current profile over the full drive cycle. As you can see, within a very short period of time, the fundamental frequency and current magnitude is changing significantly. The automotive grade silicon carbide power module should have the capability to handle these rapid changes in the operating points. Here the loss map for the full driving profile is shown, where it is visible that the switching loss is higher than the conduction loss. A zoomed-in figure shows it more clearly. Since the current in the WLTP cycle does not go even close to the rated current of the module, so most of the losses are coming from the switching. Here we have shown the junction temperature profile over the full drive cycle. A zoomed-in figure is also presented on the bottom right. The simulation model is capable of capturing all the thermal ripples, as you can see. Later on, this junction temperature data can be simplified by averaging by a sampling time. As an example, a 1 second sample junction temperature Tj is shown in the red line. This sample junction temperature or delta Tj can be fed into the lifetime model for the lifetime prediction and the reliability, which is very important information to develop an optimized and efficient power module. This slide represents the dVdt, dIdt versus the external gate resistance. From this figure, there are a couple of important points can be determined or established. First, as we know, bad busbar design, which means higher inductance busbar, can cause higher overshoot in the voltage. If very low RG is used, it can be affected by the high dVdt or dIdt at that moment. Higher dVdt or dIdt can cause module failure if the high voltage overshoot exceeds the threshold voltage. Increasing external gate resistance is an effective way to reduce the overshoot, which means reduction of dVdt. Now, nothing comes in without a price. Adding Rg causes increased switching loss. Therefore, inductance optimized silicon carbide power module with properly designed busbar is required to achieve better performance. Hence, lower external gate resistance can be used. To demonstrate this, we will be simulating the drive cycle with 1 ohm and the 5 ohm external RG. To validate our previous claim regarding RG versus switching loss, we ran several scenarios on our drive cycle simulation model. Same driving profile is simulated with external gate resistance 1 ohm and 5 ohm. This slide has energy loss information between 1 ohm RG and 5 ohm RG. From the figure, it is clearly visible that 5 ohm RG has more energy consumption than the 1 ohm RG. Also, switching energy is significantly higher for 5 ohm RG since the switching events will be slower. Thermal performance would be worse since 5 ohm RG has more losses. For better representation, we have a table showing energy consumption for WLTP cycle. From our calculation, we found out that for 1 ohm RG, energy loss is 0.12 kilowatt hour. On the other hand, when external gate resistance is 5 ohm, the energy loss is 0.21 kilowatt hour. Loss reduction from 5 ohm to 1 ohm is 42% just by using low external gate resistance. This makes a good case for investigating more into switching energy in the power module. Therefore, it is very important to have a power module with low stray inductance in addition to the busbar inductance. Hence, less overshoot, which helps to use very low external gate resistance. As a result of that, less switching loss. The energy data from the driving profile can be translated into battery range and cost. We have taken one of the EV parameters as an example. So for the energy consumption in WLTP for XM3 with 1 ohm RG is 0.12 kilowatt hour, and for 5 ohm RG it is 0.21 kilowatt hour. If we consider it is 118 kilowatt hour battery capacity and the range of the EV is 520 miles, then the MPGE can be calculated to 0.227 kilowatt hour per mile. Now, WLTP cycle is in total of 14.7 miles of range. So, total number of WLTP cycles can be driven is 35.4 cycles. Energy difference between 1 ohm and 5 ohm RG is 3.1 kilowatt hour. From this number, the range difference can be calculated as 13.8 miles, which means just by using less RG, we can achieve higher range of the EV. Moreover, cost savings and weight savings can be significant between 1 ohm and 5 ohm RG inverter as presented in the slide. That was our last slide for today's drive cycle webinar. In this slide, we have some key points to summarize our entire presentation. First, we discussed about the drive cycle simulation for electric vehicle. Although many simulation tools exist, however, not all are suitable for application simulation, and even fewer can simulate long drive cycle. It can take over days to simulate a full drive cycle. But with the help of averaged model instead of switched model, we can simulate the full drive cycle within a very short period of time, which was shown in our presentation. Another aspect of traction drive system is that it is a system with the switching loss dominated. Therefore, optimized silicon carbide like EAB450 M12 XM3 can be the best option for traction application. In the beginning, our another presenter, Blake, highlighted our evaluation kits with XM3 silicon carbide power module. The dual inverter application and evaluation kit can get you prototyping drivetrains on the dyno in short order. Thank you again for attending today's webinar, and we will be happy to answer if
All right, well, thank you, gentlemen, for a great presentation. We're now going to move on to the question and answer portion of our event. As a reminder, if you'd like to participate in our Q&A session, simply type your question into the text box located to the right of the presentation window, or go ahead and click on the Q&A icon at the bottom of your screen. Type your question in and then click the Submit button. Please note we'll get to as many of your questions as we possibly can. If we don't get to your individual question today, someone will get back to you after the program is over. So let's get started with some questions for you, gentlemen. Our first one, how fast is the average model compared to the switched model?
Thanks, Chris. This is Blake. I'll take that question. So I think it does depend, especially on your application, your switching frequency. Basically, the number of switching events that you're averaging out will determine how much faster it is. But I think a rule of thumb we can probably use is more than 10 times faster than the switched model, at least in dry cycle applications, using silicon carbide where you have relatively high switching frequency. So you would see, it probably take you a minute to simulate a minute in the switch mode model, maybe a little longer than that. And then in the average model, even with the thermals, you can probably do it in 5 or 10 seconds to get through a minute. So significantly faster. Rule of thumb would probably be 10x.
All right, thank you, Blake. And we'll move on to another question here for you. How close would the PCB prototype be to a real bus bar in inductance?
This is Hazaz. I'll take that question. And the PCB, in general, the PCB-based bus bar prototype and the real laminated bus bar have similar inductance if they are planar geometry. It means if it's a very simple design and it's a planar, then both of the geometry will have the similar inductance or strain inductance. Since the inductance depends highly on how much area of the conductors with the different polarity or overlap, for planar geometry, it would be very much close to each other. However, if we have a complex bus bar design, then for PCB, it would be tough to prototype. Therefore, for like if we have a bend in a bus bar design. So therefore, for a complicated bus bar, laminated bus bar has an advantage over the PCB bus bar. But in general, if they are same geometry and if they are overlapping the polarity of the bus bar, then it should have a similar inductance. Other things associated with it is it depends on the cost and the feasibility as well. So if we have a high power, if we need to design a high power bus bar, then PCB and even the laminated bus bar will have the similar cost. So in that case, fully laminated bus bar has the advantage for the current density as well as the temperature rise. It is more thicker. So, and thicker PCB will cost more. So it's kind of a trade-off.
All right, thank you, Hazaz. We'll move on to another question here. Again, to our audience, if you'd like to ask a question, click on the Q&A icon, type your question in, click the Submit button. We'll get to as many as we can. If we don't get to your question today, someone will get back to you after the program is over. So our next question here, why do we need an average to average the junction temperature in order to calculate lifetime? Why can't we use the raw junction temperature directly?
So yeah, I'll take that too. So if we use the peak junction temperature where we have all the ripples, then we will be underestimating our lifetime of the power module. So the lifetime models that we have is based on a number of cycles. So in our case, it would be either 2 seconds or 1 second long. So to see the equivalent stress for the model, we have to average down the junction temperatures from the repo junction temperature and look the temperature on that time scale.
All right, thank you, Hazaz. And we'll move on to another question here. Is Simulink a good replacement for Plex and Spice? And are there are there anything we have to rely on Plex and Spice?
Sure, Chris, I'll take that one Blake again. So Simulink is certainly a reasonable replacement for some of the features of Plex. It, I believe, is a bit more expensive, but if you already have it, I could understand wanting to use it. Plex does offer a block set which works inside of Simulink. So if you want to develop, say, your control scheme and those sorts of things in Simulink, you can still take advantage of Plex. So the question, is kind of what does Plex offer that Simulink doesn't? It's a bit more precise in terms of your thermals and energy calculations. If you use any of the, kind of generalized electronics simulation stuff in Simulink, they aren't really optimized the way that Plex is. So Plex will be very good, and it's very fast to model, say, a data sheet of an unknown part. And you can basically take advantage of both is kind of what I would recommend. Do look into the Plex block set for Simulink, but yes, you could do pretty much this simulation in Simulink. I think you'd be a little bit more, it'd be a little bit more work, but it would be possible. As far as Spice, I think Spice and Simulink don't really overlap. They're different tools for different purposes. I would say, if you need a Spice level simulation, Simulink won't really do it for you. But if you're trying to use Plex, Simulink could be a suitable replacement. I do believe it's a little bit more.
All right, thank you, Blake. And we'll move on to another question here. What's the output of the drive cycle simulation model? Junction, temperature?
Yes, so I'll be taking that question. Yes, the drive cycle simulation model can capture the junction temperature as well as it calculates the losses. So it's a closed loop system, as Blake mentioned. So we calculate for a particular driving condition or particular operating condition, we calculate the losses, and that loss goes to the junction temperature or temperature profile, and that increases the junction temperature, and then the junction temperature comes back to the losses and increase the losses or decrease the losses based on the junction temperature. So that's kind of a closed loop system. Yes, you're right. The junction temperature can be measured from our model.
All right, thank you, Hazaz. And we'll move on to another question here for you. Our next question, when calculating the power loss, why do you use a 3D lookup table and scale by gate resistance? Wouldn't a 4D lookup table work better?
Yes. So this is Blake again. We would say that in calculating your switching losses, you're going to see a trade-off there, where if you are linearizing against gate resistance, there's going to be a little bit of inaccuracy. So the main reason to use a 3D lookup table over a 4D is that there is a much smaller amount of data required. Is basically, if you have a particular gate resistance you want to see, you only need the data at that particular gate resistance, and you create your lookup table based on that, and then you don't even need to scale. But you could alternatively take a very large data set, perhaps if you had our TIL application kit, you could take a very large data set across several gate resistances, and you could build the 4D lookup table. I think it would be a little more challenging to implement in Plex, but I'm pretty confident it would be doable. It's a trade-off versus, how accurate do you want to be versus how much data do you need to collect to create the model. So I think that it's, for us, a 3D lookup table is pretty well sufficient, but there's certainly nothing stopping you from going further than that.
All right, thank you, Blake. And we'll move on to another question here. Why are switching loss dominated in traction applications. It says, in my opinion, regarding to additive power losses on a traction motor should be optimal switching frequency for 1200 volts, power module roughly frequency for roughly from 4 to 6 gigahertz. Kilohertz.
Hi,
My apologies.
Yes, yes. I'll take that question. So yes, you are right. If it's a IGBT-based traction drive system, then we use the 4 to 6 kilohertz. Since we are going to use the silicon carbide for traction application, then we can leverage the higher switching frequency or less switching losses in the silicon carbide. So in that case, the switching frequency can be 10 kilohertz, 20 kilohertz, even up to 40, 50 kilohertz at some point. So that is one thing, that at high frequency, the switching loss will be dominated. And the other thing is, if you see I presented one of the curve where it shows the relationship between the switching loss and the conduction loss, versus current. So at lower current, the switching loss will be always dominated. But if the current is close to the rated current of the power module, then in that case, conduction loss will be dominated. For WLTP cycle, since it's the low current region, then in that case, the switching loss will be always dominated.
All right, thank you, Hazaz. And we'll move on to another question here for you. Our next question, how much variation are you seeing in switching losses versus the data sheet values?
Sure. I'll take that one again, Blake. So it is in Plex, they allow you to enter the specific value you would like to see. So the general strategy is to put in the values directly out of the data sheet. So because of the way the lookup table works, there would be no variation in the value you give versus what it's using to calculate the thermal system. This is just, one of the simplifications of Plex, but one that makes it, I suppose, more accurate in a sense. But you certainly don't have to use the data sheet values. Obviously, the data sheet values are based on certain assumptions, such as, say, your parasitic inductance. And you could certainly, if you have a particular scaling factor in mind, take that into account before you create your Plex model. This all applies both to the way we've done the average model as well as your traditional switched model. So I think that in general, the answer is Plex just uses the value you give it. So that makes it perfectly accurate in a sense, but obviously, it is a simplification.
All right, well, thank you, Blake. That does look like all the time that we have for questions for today. I'd like to thank Blake and Hazaz for a great presentation and Q&A session. And for more information related to today's webinar, please visit any of the resource links available in the green folder icon at the bottom of your screen. And within the next 24 hours, you will receive a personalized follow-up email with details and a link to today's presentation on demand. Once again, if we did not get to your individual question today, someone will be getting back to you after the program is over. And we'd like to thank you for attending today's webinar, Optimizing Drive Cycle Simulations for Automotive Applications, brought to you by Tech Online, Wolfspeed, and Arrow. This webinar is copyright 2022 by AspenCore. The presentation materials are owned by or copyright by Tech Online, Wolfspeed, and Arrow, and the individual speakers are solely responsible for their content and opinions. On behalf of our guests, Wolfspeed and Arrow, I'm Chris Keach. Once again, we'd like to thank you for joining us, and we hope you have a great day.